Hello students, in this video we'll discuss the first fundamental form of a surface whose coordinate patch is in geodesic polar coordinates. Let's recall, in geodesic polar coordinates, we have a first fundamental form that looks like this. That looks like dr squared plus some function g of r and theta d theta squared. In this video, we'll discuss properties of the function g, okay? Now, recall also that if I change coordinates, the first fundamental form changes like this. I tilde, the new first fundamental form, is going to be the Jacobian transpose, the original first fundamental form, the Jacobian. Now, these coordinates over here are going to be our theta coordinates. These coordinates over here are going to be xy coordinates. And then what's the Jacobian? The Jacobian is going to be d what? dr dx, dr dy, d theta dx, d theta dy. And we know how to compute these things, right? So dr dx is going to be x over r. dr dy is going to be y over r. d theta dx is negative y over r squared. And then d theta dy is x over r squared, right? We've done these calculations before. I'll link to videos where I've shown how to prove those facts, but those are elementary facts about polar coordinates. And so now let's write down our change of coordinates. Now, what choice am I making between x, y, and r and theta? We're choosing the traditional ones, right? We're choosing x is r cosine theta, y is r sine theta, right? That's how we know this is just standard polar coordinate transformation. Okay, good. So now what's our I tilde going to look like? So our I tilde is going to look like the transpose of this thing first. So it's going to be x over r, y over r, and then negative y over r squared, x over r squared, times the first fundamental form, which is a 1, 0, 0, g. Good. And then times just the ordinary Jacobian, right, which is going to be x over r, y over r, negative y over r squared, x over r squared, like that. And so we'll just simplify to, this is going to simplify to what? This is going to be a x over r, negative y over r squared, a y over r, and then an x over r squared, times a x over r, y over r, then a negative yg, negative yg over r squared, then an xg over r squared. Beautiful. Now from this, I'm going to write out two facts over here. So from this, we can see that what's the E tilde component going to be? My E tilde component is going to be what? It's going to be x squared over r squared, and then plus y squared g over r to the fourth, right? So it's going to be x squared over r squared plus y to the y squared g over r to the fourth. And then g tilde is going to be what? G tilde is going to be y squared over what? Y squared over r squared plus x squared g over r to the fourth. Okay, good. I don't care about f tilde at this juncture. I just care about e tilde and g tilde because e and g both have g's in them, and I'll be able to use these equations over here to deduce properties of g. Okay. Now, clearly, if I subtract 1 from e, that's the same as subtracting r squared over r squared. X squared minus r squared is negative y squared. And if I subtract 1 from g, I'm going to have y squared minus r squared, which is negative x squared, right? So in other words, what do we have? There's a relationship between e tilde minus 1 and g tilde minus 1. And what's that relationship? Well, if I subtract 1 from e tilde, I'm going to have y squareds on top. If I subtract 1 from g tilde, I'm going to have x squareds on top, right? So I have x squareds over here and y squareds over here. So if I multiply these terms by x squared, that has to be these terms over here multiplied by y squared. Okay? This is an important relationship. Okay? Because it gives me information about the Taylor expansion of these functions in a neighborhood of the origin, right? So now let me do that next. So now I know that e tilde minus 1, I'm going to Taylor expand it. It's going to be e10x plus e01y plus e20x squared plus e11xy plus e02y squared plus dot, dot, dot. Okay, I just write down the quadratic approximation of these things. And then similarly, g tilde minus 1 is equal to g10x plus g01y plus g20x squared plus g11xy plus g02y squared plus that to that. Great. Now, the key feature is that if I multiply this equation over here by x squared and this equation over here by y squared, those expressions have to be equal, right? Because of this equation down over here. So what's our conclusion? Our conclusion is that if I multiply this expression by x squared, this turns into an x cubed. If I multiply this expression by y squared, every term will have at least a y squared and no pure x terms, right? So in other words, this term is gone. This term is gone by the same reasoning. This term is gone. This term is gone. Why so? Well, because if I have an x squared y over here, and then over here, I don't have any x squared y's, right? So because I only have y squareds over here. It turns out the only coefficients that are going to exist, now this is going to be an x to the fourth. There's no x to the fourth down over here, so that's gone. That's gone as well. Now what happens over here? This is going to be a y squared x squared. And this term over here is going to be an x squared y squared. So these two terms are the first terms that survive, and everything else goes away, right? And so what's our conclusion? Our conclusion is that E02 has to be equal to G20. So, hence, this implies that E tilde minus 1 is some number times y squared. I'm going to call that number k, ky squared, plus little o, that's a little o, of basically r to a power, r squared. Things that decay that go to 0 faster than r squared, which is x squared plus y squared. Okay, so that's what little o means, right? And now, what do I know about e tilde minus 1? E tilde minus 1 is given by this expression over here. So e tilde minus 1 is really negative y squared over r squared. So by this equation over here, this is going to be equal to what? This is going to be equal to so if I subtract 1, this becomes a negative y squared over r squared. Negative y squared over r squared plus g y squared over r to the fourth. Beautiful. I'm going to divide everything by y squared, and if I divide by y squared, this turns into a little o of 1, right? So that tells me, therefore, that k, because y is gone now, plus little o of 1 is equal to negative 1 over r squared plus g over r to the fourth, okay? So if I multiply by r to the fourth, this becomes an r squared, this becomes a k r to the fourth, and that becomes a little o of r to the fourth power, right? So this automatically implies that, and this is the key, this is the main fact over here, that g is r squared from this term over here, plus k r to the fourth plus little o of r to the fourth, okay? Beautiful, okay? So the function g in the first fundamental form of my original metric and geodesic polar coordinates, I can now have the first two terms in the Taylor expansion of this. Now, of course, if these terms were gone over here, I would just have the ordinary first fundamental form of the plane and polar coordinates, which is cool, right? But I have higher order terms. Now, my question becomes is, what is this value of k over here, right? Well, if you recall from Calc 2, how you do local square roots of these things, right? I can do a local square root of g, so what's the square root of g going to be? Well, the first term in the square root of g has to multiply to r squared, so that's going to give me just an r. Now I have an r on both terms of my square root, and so the next order term to get to r to the fourth, well, what power of r times r will give me an r to the fourth? That is r cubed, so it's going to be in half of that, right? That's the square root algorithm, 1/2 k r cubed plus little o of r cubed, like that. Okay? And let's just check. If I square this expression, what am I going to get? I'm going to get an r squared. Then I'm going to get some term that looks like higher order r if I square this term over here, r to the sixth. If I do this times this, what do I have? I have r to the fourth times k over 2 plus r to the fourth times k over 2. That's exactly k times r to the fourth. So we got the square root. Now, remember that these things are all centered at r equals 0, right? So this, of course, is the center is r equals 0. And now I know how to compute. I know what the Gaussian curvature is, right? So recall the Gaussian curvature is given by what formula? K, all right, K, capital G for Gaussian curvature is what? Is -1 over the square root of g times the second derivative with respect to r at r equals 0 of the square root of g. So what's this going to give us over here? Well, that's going to be a -1 over r plus k, 1/2 k r cubed plus little o of r cubed. That's the 1 over square root of g. The second derivative of this thing, the second derivative of r is going to be 0. The second derivative of this thing is going to be what? It's going to be a 3/2 and then a 3. So this is going to be a 3kr plus what? Two derivatives of this gives me little o of r, like that. Okay? And I'm doing a limit, what? I'm evaluating this at r equals 0. And the meaning that means, of course, that we're taking a limit over here. So what's the conclusion? The conclusion is that this limit is what? The leading order term is r, so I have an r over r, so I get a -3k. So this is -3k. So this limit over here is -3k. And therefore, this k coefficient in my fundamental form is negative the Gaussian curvature over 3, right? So now we have our final result. Our final result is that this g over here is really r squared, and then minus the Gaussian curvature over 3, r to the fourth plus little o of r to the fourth power. Beautiful. So the Gaussian curvature is acting as a fourth order correction in our local Taylor expansion. So now what we can do is let's go back to our original metric over here. What we can do is we can now update our geodesic polar coordinate metric and state what it actually looks like. So our geodesic polar coordinate metric has the following form. I is dr squared plus r squared minus the Gaussian curvature over 3 r to the fourth plus higher order terms o r to the fourth d theta squared. Beautiful. This formula is extremely important because it tells us how the area and circumference of these geodesic circles, the area inside a geodesic circle or the circumference of a geodesic circle, changes as the Gaussian curvature changes. So the Gaussian curvature is telling us, giving us more information about the local structure of the circumference and the area of these geodesic circles. Thank you very much.